Hey everyone, this is part 2 of Autonomous Agents 101. If you've not been through the first tutorial, it might be handy to look at that tutorial first. In this tutorial, I'm going to be going into quantization, what that means and how to use it to make interesting patterns with agents. Okay, I'll just go through what we had before. On line 154, we have our agents array. On line 156, we have a for loop where we push agents onto that array. An agent is another array of 3 vectors, a position, velocity, and scale. So we add a position using this, a velocity of downwards with that, and a scale of 1 to 1. All of these functions are modular functions where we can put in our draw loop, our agents, and it does an action on all of the agents inside that group. And so we've got an integrate, we've got a random turn. I modified this since the last tutorial, so the random turn has a turn min and a turn max, which is put in here, so the agents can turn at minus 0.1 radians to 0.1 radians. And yeah, I think that's about it. Okay, so let's dive in. So we're going to be looking at quantization. What is quantization? So quantization is a little bit like rounding a number. So if we have like an analog number or a floating point number that goes from 0 to 10, and it can have decimal places, and if we round that, we get an integer of either 1, 2, 3, 4, all the way up to 10. And this can be very, very useful. So for the first extra agent processing function that I'm going to make an integrate quant. Quantizing integrate. So what that's going to do is, rather than letting an agent move in any one of its directions, in analog in all directions, like this current one where we end up with agents creating wiggly lines, I'm going to constrain them to a limited number of directions. So let's jump straight in and start writing some code. Let's integrate quant. So we want to pass in our agents, same as we did before. We want to do almost the same as what we did here. So just put that here. So because I'm going to be modifying the velocity vector in order to quantize it, I don't want to actually modify the actual one in the agent. I want to have the agent so that it's got its analog movement, and then I want to quantize that movement after the fact. I think the reasons for this will become a little bit more clear as I get into it. So let's remove that, and so for this I'm going to need a temporary vector. So I'm going to go let's underscore temp equals v2. So we've now got our temporary vector, and I'm going to populate that temporary vector. But let's leave that for a second. Let's first off, let's create our quantized value. So first off, we'll need to get the radian value out, and we do that with v.rad, like we did on a few of the other processes, like down here for the random turn. So a vector's turning angle is anywhere from 0 all the way up to tau, and tau is 2 times pi, so everyone knows that pi is a magic number. So in order to quantize it, what I want to do is I actually want to divide it by tau. So what that does is, instead of going from 0 to whatever tau is, it now will go from 0 to 1. So now we've got it from a 0 to 1 value. What I can do is I can then multiply it by however many steps that I want. So let's put a steps value in here. And so now we're timesing it by steps. So now we'll have a value that, instead of going from 0 to 1, it will go from 0 to the number of steps that we want. And this is really useful because now I can just use literally the equivalent of math.round. So in the construct platform, you don't actually have to put math.round, you can just put round. So I want to round that number. So now I end up with the number snapping to the closest integer for the number of steps. So now we've got that, I need to put it back into like a 0 to 1 range, but while keeping the rounding or the steps that's been created by that round function. So in order to do that, it's pretty straightforward. I just need to divide it by steps. And then the final step is we just multiply that by tau. So now it's back within the tau range for the radian. I want to maintain the velocity's length. So I'm going to go len equals v dot len. And now I need to populate my temp vector. So underscore temp dot circ. I'm going to put in my rad value. So now this radian value should now be shifted into discrete steps, however many steps gets put in here. So if I do that and then multiply by the length, whatever length the vector was before, it will be the same length, but with the new radian value. And then the rest of it is basically the same as the normal integrate, where I just add, instead of the velocity, I add this new modified velocity direction. Okay, so let's put that in place and see how it goes. So I want to remove the old integrate. I'll use this new one. I'm going to make it so that it can only go one of 6 directions. So let's see if I've coded that up right. So we can see these are all now branching out in an interesting kind of circuitry-like patterns. So yeah, we're getting a kind of hexagon-like pattern. Let's just change that number and just to 3 so we can see. So yeah, they're only coming out left to right, because none of the velocities are pointing upwards. We're not really getting many upwards. And if I've got 4, it should align with the axes of the canvas, and we should have like kind of a sideways circuitry pattern. So that's pretty cool. Okay, next I'm going to make a quantized draw function. So I'm going to apply the same kind of idea as what we've done with the direction, but I'm going to apply it to the position that the agent is drawn at on the canvas. So let's go down to where my previous draw function is. Oh yeah, I actually added an additional color draw, just in case people wanted to see how that could be done. That's in the tutorial, that's in the example on the BlockGen website. Okay, so let's make ourselves a function. Let's draw quant equals, we want to put in the agents, and then we want to put in the number of like steps. So how I'm seeing this steps is, this is going to be the number of steps where pixels can be drawn over the canvas. So the canvas in its normal state is a 1000 by 1000 pixel canvas. So the kind of numbers I'd want to put into steps is like, 200 or 300. So it's smaller than the resolution of the canvas, so that we can see like the patterns more easily. So let's just jump straight into it. We want something very similar to that. Only I'm going to reinterpret the X and the Y positions. So I actually want to do something very, very similar to what was done in the other quantize. So we want to calculate our X. So p.x is our current X, and that is, like I mentioned, an X value which is over the entire X and Y of the canvas, which is 1000 by 1000. So if I divide that by 1000, it'll be 1000 times smaller, which means it's now within the 0 to 1 range, which is handy. So once again, now it's in the 0 to 1 range, I can multiply by the number of steps that I would desire. So now it's multiplied by the number of steps, I can just do a round to the nearest integer. So now we've got however many steps there are, and it's rounded to that integer. So next, I want to pull it back to the 0 to 1 range. So if I divide it by steps, the result of that, we now have it in a 0 to 1 range, but it's still got the quantizing where it snaps to however many steps there are. And then we just re-multiply it by 1000, and it's back within the original range with the quantizing in place. Now, in this platform, for the size of the screen, we have a constant that's defined, so that's called px. So I can import px in both of those. So if you did a console.log on px, you'd find out it was just 1000. It was 1000, and it helps to save space to put things in like this. So we've now got our x. So now let's do the same with our y. Done, and then we've now got those values being plugged into the actual rectangle, the black rectangle that's drawn. Okay, so let's put that in place here. Let's go for 300. So let's see if that works. Okay, so what we can see now is we can see that it's drawing not on every pixel, it's snapping to the nearest spot, which is giving us this nice little grid-like pattern. I'm also going to switch out of rectangle and I'm going to draw a circle instead. So to draw a circle, it's actually very similar to how you draw a rectangle. There's just a few extra values. So if I just comment that out, instead of rect, it's ELI for ellipse. All of these values are exactly the same, except for we need 3 additional values, and they are it's like starting angle, is it starting rotation, finishing angle, or something like that, but all you need is a 0, and then the full, rather than having an ellipse like a pie chart. If we do it to tau, we get a full circle. So this is what you need for a full circle. 0, 0 tau. So if we now look at it, we actually have a pattern of, this is made out of circles. So it's looking pretty interesting. Okay, so next we're going to look at agents that go outside of the bounds of the canvas. So some of these agents go outside the bounds of the canvas, and we might want to keep them on by, in this case, I want to, any agent that goes off that side of the canvas, I just want it to come back onto the other side of the canvas. So let's write something that does that. So I'm going to call this screen wrap. Let's screen wrap, and we put in our agents. We want basically that. And we want to work on the p.x and the p.y values. So we already have a function in the code base called wrap that's super handy. So wrap, I want to put in the p.x value, and I want to go from 0 to 1000. Now, if you remember from earlier, we have a constant for the size of the screen which we can use, so that's px. So we want the x value to be wrapped within that. So if the x value comes in and it is 1001, it will get turned to 1, and it'll basically go from over here, which is slightly off the canvas, to slightly on the canvas on this side. And so we want that for both our x and our y. So that's pretty much it. That's all we need for a screen wrap. So if I put this in here after the integrate, so the integrate's what moves agents, so that's a good place to put a screen wrap, and then we put in our agents. We don't really have many agents actually going off the screen, so let's just increase the size of this spiral so that we can see this working a bit better. So we have a spiral that is 400 pixels from the center, so that's the highest point, that's this part here. So if I make that so that that's twice as big, that should go way off the screen and we should be able to see very clearly. So let's try that. Okay, we have a syntax error, let's see what's going on here. There we go, missed an equal sign. So as you can see, the agents that were going off the side of the screen are now just being put back onto the side, onto the other side, and we're getting this spiral that goes off here, comes onto here, all the way up there, to here, and then to over here. So yeah, that's working pretty good. Okay, I think that's a good place to end this tutorial. Thank you very much for listening, and have fun creating things.